Okay, we can get going. Any questions from anyone before we get started? Technically or logistically or anything like that. Hopefully folks have found the sign-up sheet for final project demos and have begun signing up. Let's actually just take a look quick. In the event that you have not yet signed up for a demo, please do so, just so that we can get schedules figured out. It looks like there's a lot of groups that still need to sign up. And again, like I said, if you're interested in doing this early demo, let me know and we'll find a time to schedule that. But if you have not yet signed up for a demo, do please sign up. Okay. Anything else? Yeah. No, you don't. Yeah. The progress report for that, whatever the last week is that you're working on the project, it's just going to be the demo. Yeah, so there won't be a deliverable associated with that other than the demo. Any other questions? Materials continue to roll in that people have ordered. Like I said, I'm just going to be bringing those to the lab with me, and I'll sort of array them on an unoccupied bench so you can paw through those and see if anything in there belongs to you. Otherwise, my plan for today was to continue the conversation that we started last time. I'll remind you that last time we had just started talking about communicating over a Wi-Fi network by way of UDP. And we started that conversation by speaking in the abstract about how this process generally works, what happens when you plug in a router and set up a Wi-Fi network, and then what happens when some device connects to that network. So we talked through that in the abstract in order to lead to a conversation about talking specifically about how one does this with a Pi Pico W. And so that's the conversation I want to have today. The libraries that we will be making use of in order to do this, I guess let me just speak for a moment in general about the Pico W Wi-Fi stack. This, as I've said a few times, this is one of those 3 external libraries that the Raspberry Pi folks ported to the RP2040. This one is LWIP, written by Adam Dunkels and some others. The other third-party libraries include BT Stack for Bluetooth communication, which we talked about a bit, and then Tiny USB for making the RP2040 behave like a USB device. The Pico W Wi-Fi stack, like all of these sort of pieces of software infrastructure associated with the RP2040, is hierarchical. There does exist a very low-level driver for communicating with and configuring the external Bluetooth and Wi-Fi chip, the CYW43. It is probably the case for almost all of you that that low-level driver is a layer of abstraction or two beneath where you'll probably be doing your engineering. But I just want to let you know that it exists. And the slightly higher levels of abstraction where you'll probably be doing your engineering make implicit use of these low-level drivers. We will, however, so the lowest level driver is this CYW43 driver. There exists a Pico library which implements some functions using that low-level driver called Pico CYW43 Arch. This is probably the lowest level of this stack where you'll be doing engineering. And in today's conversation, which is going to start with how we actually connect an RP2040 to a Wi-Fi network, that connection is facilitated by way of this library. Once we're connected, there's a higher level Pico LWIP library. That's the wrapper for the third-party LWIP Wi-Fi stack. That's the library that we're going to be used to facilitate UDP communication through the network, or if you wanted to, TCP communication through the network. So just in summary, this is hierarchical. Lowest level is CYW43 driver. You probably won't work there, but you will, however, probably interact with the Pico CYW43 Arch library in order to connect to a network. Once you're connected, we'll be mostly making use of the Pico LWIP library to facilitate communication. So how do we actually connect? The first thing that we do is you have to initialize that external hardware, basically turn on the Wi-Fi chip and get it going. We do that by way of a function in that Pico CYW43 Arch library. Actually, you can do it by way of a couple different functions. One of them is this arch init with country, which takes as an argument a 32-bit country code. You may recall from our last conversation that it's sometimes the case when you connect to a network or when you set up a network that you specify the country that you're in. This is how the device knows which channels are legal for it to occupy and what power levels are legal for it to use. So we might set it up with the country code. We may alternatively just call arch init with the void argument. In this case, it will use the default country code, which if you dig through the SDK, you will discover is configured to worldwide, which is just to say it'll use the channels and power levels that make it legal around the world, right? But we could also substitute in there the USA country code if you wanted to. What we then need to make a decision about, it is the case that these Pico Ws, they can act as stations. That is to say, they connect to a network and communicate through it. They can also behave as access points in which they generate a network that another Pico W or your phone or your laptop or whatever can connect to. And so we have to tell the device whether we would like for it to behave as a station, it's going to connect to a network, or whether it's going to act as an access point and have other things connect to it. In our case, for purposes of this conversation, we're going to talk about setting this thing up in station mode so that we could, for instance, communicate to our laptops through Red Rover or something like that. Okay, so both of our devices are going to communicate to some network, and we're going to talk through them. We do that, again, by way of just a function call to that Pico CYW43 arch library. We say Pico CY, that's a typo, CYW43 arch enable station mode. That tells the system we're going to be a station. And by the way, as always, we're going to look at some demo code of this in a moment to try to tie it together, but I just want to talk through the steps first. We then connect to the network. And connecting to the network, we could do so in a few different ways. There's a catalog of 6 different options here for how we might connect to a network. The only difference between these various things are things like, do we want to attempt a connection in a blocking fashion? That is to say, here's the name of the Wi-Fi network I want to connect to. Here's the password for that Wi-Fi network. Please sit here and block until you've successfully connected to the network. Oh, and by the way, this last argument is the security protocol specification. Okay, so do we want to sit and block? The second argument here, the connect BSSID blocking, also as an argument takes the MAC address of the device to which you're connecting. Sometimes that's a nice security feature. Okay, so we could connect in a blocking fashion. We could alternatively connect by either of those two mechanisms in a timeout fashion, where you say, please try for X number of milliseconds to connect to this network. In the event that you don't succeed in that number of milliseconds, then fall through and do something else. It allows for the code to continue after a certain amount of time has passed. Or your last option here with the async suffix says, please go off and try to connect to this network. I'm going to carry on doing other things, and you just let me know when you've successfully connected. By way of an interrupt, as it turns out. Okay? And so we can connect either in a blocking fashion, a timeout fashion, or an asynchronous fashion. Once we have connected, remember that when a device connects to a network, the router for that network will provide the connecting device with a few pieces of information. It's going to let the device know what its IP address is. Its IP address gets assigned by that DHCP server, right? So it's going to be told what its local address is. It's going to be told what the mask is for that network. That is to say, for a given IP address, which parts of that IP address represent the network and which parts represent the device names on that network. So it gets told what the local network's mask is. And lastly, it gets told what the local network's gateway address is. And I'll just remind you that local devices connected to a local network, if they want to communicate with one another, so they specify the IP address of some other device with which they'd like to communicate, every device on that network can tell by way of the network mask whether or not that destination device is on the local network. And in the event that it is, your packet just sort of goes straight to that device. It doesn't bother the gateway. But in the event that your local device specifies a destination IP address that is outside the local network, it will get forwarded to the gateway device on your local network, which acts like the door to the broader internet. And this is a role that is more often than not played by your router. Usually your router assigns itself the .1 IP address on the local network, and generally speaking, it makes itself the gateway, so that, if your Pico W tries to send a message to, I don't know, your home machine on your home network, which has an IP address that lives outside of that local network, it'll get routed through the gateway here. Just remind you, by the way, that if you do try to do that, you will specify the public IP address of your home router, and you'll specify a destination port on that router. And then at home, you'll have to configure your router for port forwarding. So anything received on this port will get routed to the following local address on that network. So when we do connect, right? So when one of these functions finally clears and we connect, what we will have received is these following pieces of information. And there's infrastructure in the LWIP library that allows for us to observe these various things and print them out, for instance. And we can do that by creating a Pico LWIP object called IP address _ T. As the name suggests, this is a data structure in the LWIP library that keeps track of IP addresses, right? So it's just a handy data structure for that. We're going to call this thing IP. And then there's a series of macros that allow for us to interact with these kinds of data structures. What we're doing in this case, let me just see here. What are we doing? I'm sorry. So we can print these things out in the following way. These printf statements, where we're printing IP, colon, and then as a string, we're using the following provided function to print out the netif _ default. Turns out that when you connect to a network, the network information gets stored in a struct named netif _ default. That is just the default struct name for where this information lives. There's some macros that allow for us to observe and print these things out. That's what's going on there. So the first macros in there are accessing the IP address, net mask, and gateway information contained within that netif default struct, different pieces. And then the outside macro here is just configuring that as a string so that we can print it out. Okay. And then I was getting ahead of myself. What we're looking at down here is it may be the case that once you connect to the network and get some default configurations, IP address or whatever, it may be the case that you want to pick your own IP address, your own static IP address, and you can do that. You do it in the following fashion. You create an IP address object, you give it some name, and then by way of some provided functions, netif set IP address, which takes as an argument the default IP address struct object for our Pico W and the new IP address that we would like to assign. This configures our IP address to be whatever we would like for it to be. So what that is handy for is it may be the case that that devices connecting to your Pico device assume a static IP address, right? They assume that every time this thing boots on, it has the same name on the network, so that it doesn't have to go re-look up that name. You can enforce that that is indeed the case by assigning yourself your own IP address after you've connected. You better make sure that it's an IP address that's compatible with your local network, of course, but you can certainly assign your own IP address. I will just mention, it might occur to you, why are we allowing for DHCP to assign us an address and then we're changing it? Wouldn't it be easier to just skip the whole DHCP process? We'll just give ourselves an address. That is possible in principle. It would require some modification of the SDK. The way that the SDK is set up, my recommendation for the easiest way to give yourself an IP address is allow for DHCP to assign you one and then just change it. That's the path of least resistance here. And then, of course, if you wanted to, you could modify the gateway. You could modify the net mask or the network mask as well, with caution, of course. Any questions about this? And it may be the case, just by the way, given that every time you connect to a network, there's a series of of things that you're going to want to do, right? So every time you connect, you're going to initialize the hardware with some country code probably. You're going to put the device into station mode. You're going to connect to the network. It's going to give you back an IP address, a net mask, a gateway. Maybe it's the case that you want to change some of those, but it's some set of procedures that you want to have happen every time you connect to a network. It's a good idea to wrap all of this into a function that you can then just reuse. And so here would be an example of such a function. The libraries that we would need to include in order to do the things that I just described include standard I/O, the Pico standard lib library, and the Pico CYW43 arch library. The Pico's wrapper for that low-level driver. And in this connecting function as arguments, probably it would make sense to create a function that as arguments takes things like the country code, the name of the Wi-Fi network that you want to connect to, the password for that Wi-Fi network, and the security protocol that you would like to use. If you put all of this into a header file, which is probably a nice idea, it may be the case that in that header file you make these various things easy to change global parameters, for instance, right? So you would make the Wi-Fi name some string that represents your Wi-Fi name, red rover, or if your phone's generating a hotspot, it would be the name of your hotspot. Put your password there as a string. There's the USA country code, just incidentally. There's a whole library of these. And for your security authorization, it's probably the case that all of you want to use the WPA2 mixed. This gives you maximum compatibility. And so it's probably the case that you'll want to use that. And then you call this function with all of these things as arguments, and you're going to basically go through the process that I just described. You're going to initialize with the country code, checking for errors. This is turning off the onboard LED. We put the device into station mode, print a little message that we're going to try to connect. This particular implementation uses the blocking Wi-Fi connect function, which as arguments takes the name of the Wi-Fi network to connect to, its password, and its authorization settings, its security settings. It'll sit here and block and try to connect forever because we're using the blocking option. Once it connects, we fall through and turn on the LED. It's just some visual indication that we've connected to the network. And then the last thing that this function does is print out to the serial terminal the IP address that we've been assigned, the net mask, and the gateway. Once this is set up, we are now in a position to do UDP communication or TCP communication or whatever, right? We're connected to the network. Any questions about this? Perhaps it stands to reason that if your device is an access point, you would specify the name of your network and its password, right? That you're generating. As a station, you pass those in as arguments. And as I've mentioned a few times, if you're doing this for your project in lab, my strong recommendation, at least to start, is use your phone's hotspot. It's easy to connect to. We can get you connected to the Cornell network. There's just a couple of extra steps involved to make sure that we don't do anything that the IT folks don't like. But your phone, you can just connect and get things figured out locally. And then if for your final demo you want to connect to the Cornell network, we could do that. Okay, any thoughts here? I'm going to talk next about UDP communication. Once we start talking about UDP communication, we are, just by the way, out of this lower level of the Wi-Fi stack and up into a higher level, which is the LWIP library. And I thought that we would have this conversation by taking a look at some code. Let's do that. Let's see. This code, by the way, I've been putting this together, so it's not posted online just yet, but I can absolutely get it posted. But it's based on some other examples that Bruce and others have posted. So in any case, I'll just point out first of all that over here in the files involved in this particular project, there is a connect.h header file that includes exactly that, function that we were just looking at. Okay, so this is the library that we'll include in order to connect to a network. And then this example here, all that this example is doing, we'll go through it in detail in a moment, is it connects to a network. Once it connects to that network, it sets up a port through which it can receive UDP packets, and every packet that it receives, it will print out the payload as a string. So it sort of makes an assumption that we're sending it strings, and it will print out each string that it receives. And also, it will prompt the user for strings that we can enter into the serial terminal, and it will send those strings out to some destination UDP address. And so in practice, what this ends up looking like is you could set up your phone's hotspot, you could connect the Pico W to that hotspot, you could connect your laptop to that hotspot, and through that hotspot, we can send strings to the Pico W that it will parse and print, and we can also send strings back from the Pico W to our laptop and print it out on our laptop. So structurally, what this looks like is some includes up top. Here, some macros, which names that suggest their utility. We are specifying, for instance, a UDP port. We're going to use that port to receive messages. We're specifying a beacon target. That is the destination IP address to which we will be sending packets. We're specifying a maximum length for these messages, sort of arbitrarily, as 127 bytes. We're declaring a data structure here that I'll talk about in more detail here in a moment, but for the time being, I'm just going to wave my hands and say, this is the data structure that we use to maintain the state of a connection, a UDP connection. We're declaring one of these globally. We're making a big array of bytes in which we will store messages that we receive, the payload of messages that we receive. We're making a semaphore that we're going to make some use of. This is our receive callback function. I'll show you in a moment precisely how we do this, but we set the system up such that every time we receive a message that is meant for us, this function will get called. This function is going to copy the payload of the packet that we received into that character buffer, signal a thread to do something with it. It's going to clear the payload buffer, and then free this pbuff object that I'll talk more about in just a moment. It's these pbuff data structures that facilitate the communication of data up and down the LWIP stack locally. There's an initialization function here that sets up the UDP receive port. We'll talk about that in detail in a moment. And then we have two proto-threads. One proto-thread that is just going to print out all the data that we receive whenever it's semaphore signaled by that callback function that we were just looking at. And then a second proto-thread that will prompt the user for some message. And then once the user enters a message, it is going to put that message into one of these pbuff structs that's used for managing data up and down the stack and send it off to a specified destination port and IP address. Look at how that's done in a moment. But we have a UDP initialization function, a UDP receive callback function, a thread for receiving data, and a thread for sending data. But let's start down here in main. We initialize standard I/O. We call our connect Wi-Fi function with all of these arguments. Remember, this is blocking, so it will sit here and wait until we've connected to a network. Once we've connected to the network, we're going to initialize our semaphore that we are using to signal from the UDP receive callback function to the receive thread that a message has been received. We call our UDP initialization function. That's the next thing that we're going to take a look at. We add our send thread to the scheduler, our receive thread to the scheduler, and restart the scheduler. Okay. So really all main is doing here is connecting to the Wi-Fi network and then calling this function that's going to initialize our UDP receive port. We're going to take a look at that here in a moment. Are there any questions about this before I move on? Okay. So what happens when we call this? How do we actually set up the UDP receive? We do it in the following way. The first thing that we do is we configure this global object. So what we have created here is a pointer to an object of type UDP underscore PCB. The name of that pointer is UDP RX PCB. PCB stands for Protocol Control Block. In LWIP, it's these data structures, as I alluded to earlier, that manage all of the state for a UDP connection. So the state involved in such a connection would include local IP address, for instance, local port number, perhaps remote IP address, perhaps local port number, and some other things like callback functions and so forth. But it's these protocol control blocks that are being used to hold all of the state for a connection. In the event that we have multiple connections, we'll have multiple protocol control blocks. And in fact, in this example, as we'll see, we do. We have one protocol control block that's going to handle data coming in to us, being received, and another one that's going to handle data being transmitted out. Okay? But this, as you notice, is just a pointer to such an object. There does not, as yet, exist the object to which it's pointing, right? So when we, down here in the UDP initialization function, when we do the following, we are actually creating the object to which UDP RX PCB is pointing. We're creating that protocol control block struct. And we're specifying furthermore that the communication through this particular protocol control block can take place through any type of IP, IPv4, IPv6, whatever. Okay, it'll handle any of them. If you peek under the hood a couple of layers here, you will find functions with names like PCB alloc. It looks a lot like malloc. And then you'll notice, if you may have noticed as I was scrolling through here, we'll get to it in a moment, but there's these pbuff free sorts of things. So it kind of looks like we're doing mallocing and freeing, which you may have heard me say a few times throughout this semester is a spooky thing to do on these systems. It's generally ill-advised to be mallocing and freeing on these tiny little embedded systems for a number of reasons. One of them being you're quite susceptible to memory fragmentation on these devices. So it sets you up for non-deterministic runtime errors. System's working, boop, and it just stops working. And so you look at this and you might have a little bit of concern that, boy, it seems a little bit weird that we would just be globally declaring a pointer and then at runtime allocating the thing to which we're pointing. That seems sort of against a lot of what we tend to do with these systems. If you peek quite deeply into here, what you will discover is that the PCB allocation, the PCB freeing, and the pbuff allocation, the pbuff freeing, they don't make use of the standard malloc and free C functions. Instead, LWIP has implemented their own versions of malloc and free that are different in some interesting ways. When you compile an LWIP project, there's a whole bunch of configurations that you can make to this project by way of some header files that I'll point you to here in a moment. But one of those configurations is how much memory you would like to give to LWIP. You give LWIP a certain amount of memory, and that's the amount that it is allowed to play with when it is allocating and freeing its own data structures that it uses. So one of the risks that you sometimes set yourself up with these tiny systems using, for instance, malloc, is you can malloc your way into some dangerous parts of memory. The LWIP implementation prohibits that. It does not totally prevent a situation in which you can get memory fragmentation. That is possible still in these systems. And if you're doing lots of allocating and freeing of these pbuffs that I'll talk about here in a moment of a bunch of different sizes, there's a strategy that you can use that I'll discuss to mitigate this risk. There exists something, in fact, called a pbuff pool. These are statically allocated buffers of specific sizes that you can go use instead of allocating new ones. As it turns out, I'll just mention, in the case of these protocol control blocks, when we allocate a new protocol control block, for this particular data structure, what LWIP does is at compile time, it makes a pool of them. So there's a bunch that just exist in memory statically. For these PCBs, when we say, please allocate one to me, what we're actually doing is going to one that already is created in memory and just grabbing it and using it. And then when we call free, we're not actually freeing the memory associated with these PCBs. What we're instead doing is saying, please just now mark it as unused. I'm not using it anymore. Somebody else can use it. So in the case of these protocol control blocks, we aren't actually doing any runtime allocating and freeing of memory. For the P-buffs, there is some of that, and I'll talk about that in a moment. That's getting perhaps a one layer below of most immediate engineering relevance, but it's worth knowing, I think. In any case, we create the UDP protocol control block to which we're actually pointing. We do some error checking here. Presuming that that all went okay, that is to say UDP RxPCB is not null, what we then do is call a function UDP bind. UDP bind associates this particular UDP control block, protocol control block, with a specific local IP address and port. So what that implies is any information that comes to us through this IP address and this port will be sent to this protocol control block. For receiving UDP information, we must bind a particular port to a particular protocol control block so that when something comes to us, there exists a protocol control block infrastructure to do something with it. Otherwise, the system has no idea what to do with the information that it receives. As it turns out, for sending information, because UDP is connectionless, there's no ACKs or anything, we don't actually have to bind to send, but we do have to bind to receive, okay? So what we were saying here is, please, anytime you receive something that has our IP address and this port listed as the destination, please send it to this protocol control block. And then as a last step, we have to actually tell this protocol control block what to do with the stuff that gets sent to it over that IP address and port. And what we do in this UDP receive function here is we say, please associate this function as our receive callback function. So that is to say, every time somebody sends a UDP packet to this IP address and this port, we'll send it to this protocol control block. And in this line here, we're configuring this protocol control block with a receive callback function. So now anytime something is sent to this port at our IP, it'll get sent to that function. What does that function do? Any questions before I move on, just incidentally? So in very much the same way, you may recall from our discussion of BT stack that these callback functions, their form is specified in the library. So that is to say, LWIP will call our receive callback function, and when it calls it, it is documented. The arguments with which it calls such a function are documented. So when this function gets called, it will get called with an argument that represents the protocol control block. It'll get called with an argument that is a pointer to the P-buff. Remember, this is the data structure that's used for shuffling data up and down the stack. It's going to call our callback function with a pointer to a P-buff that holds the packet that we just received. By the way, when we receive it, what LWIP actually does is grab one of those P-buffs from the pool, one of the pre-existing ones, and shove the data into that, and then give us the pointer to it. Here's where I put your data. It's in this P-buff. And then it'll get called with the IP address from which we came and the port address. Okay. And then all this function is going to do is do a mem copy from the payload field of our P-buff struct to this character buffer, this byte buffer received data, how much, the maximum message length. We're going to signal that receive thread down below that we've just received a packet, go do something with it. We're going to clear the payload of the P-buff that we just gathered, and then we're going to free it. Freeing it means we're done with that particular pbuff, put it back in the pool. Somebody else can use it now. These pbuffs, like I said a couple times, these are the data structure that manage information movement up and down through the LWIP stack. They hold the payload data and they hold some metadata about that payload. So of course there's a field called payload, and then there's information about who did this packet come from, what IP address, what port address, what was its destination, and some other meta information about the packet. That all gets wrapped up in these pbuff objects. Okay, any questions about this? So then let's just complete the story associated with receiving messages. If we go down to our proto-thread receive thread, all that this thread does is wait on that semaphore from the receive callback function, and then it prints out the contents of that received data byte buffer. That's where we copied the payload, the pbuff payload into, right? And so if we're sending strings, what we observe down here is strings. I demo this, but I have to switch my computer then to my hotspot, and I worry that the connection to the remote folks would fall out. Okay. Questions about that? So just point out that there's actually not that much infrastructure here. So UDP communication is pretty lightweight. And it's pretty handy for doing things like if you wanted to send command sequences, from your laptop to, some network connected Pico W or something. It's a nice way to do it. It can sort of replace like a serial input, right? You can also, of course, stream data if you wanted to. Okay, so how do we send stuff? Everything associated with UDP send is consolidated in the send proto-thread. Here, after we, create our thread, we create a local different proto-thread control or a protocol control block, calling this one PCB. Make a new one. Okay, so here we're making a pointer to such a thing. In UDP new, we're generating or actually grabbing the thing to which we're pointing. We create an IP address object, and here we are setting the value of this IP address object to be the IP address to which we would like to send information. In this little demo, it would be perhaps the IP address of your laptop, for instance. And then we do some familiar looking stuff. We use the proto-threads serial read, serial write features that you all have been using in order to prompt the user for some input. Use serial write to print out that prompt. Serial read sits and yields until the user has entered something. Okay. Once the user has entered some string, what we then do is allocate a pbuff. So we're specifying here, okay, that we would like to declare a transport pbuff. They come in a few different flavors. Transport means I'm going to be using this to transport information. We specify the length of the payload for the pbuff, and we specify from where in memory would we like for this pbuff to be either grabbed or generated. We have a few options here. It's often the case when you're sending UDP messages that you specify pbuff RAM. When you specify pbuff RAM, it will actually do something approximating a malloc, LWIP's version of a malloc. It will do so from the sector of memory that you have allowed for it to do it from. As I suggested, we could alternatively there specify pbuff pool. If we do pbuff pool, what it will do instead is go to the compile time generated collection of pbuffs and grab one of those to use. The trade-off here is that all of those ones that we generate at compile time, they are of course of fixed size because we statically allocate them, which means that we may be grabbing a pbuff that is bigger than we would actually need to send our message. It's a trade-off, right? On the other hand, perhaps it's a little bit more less runtime risky. You're not doing any kind of allocation or anything, okay? And you get to and just incidentally, in the configurations here, you can specify some of the features of this pbuff pool. Please generate this many pbuffs in the pool. Please make them this size and so forth. If you try to grab from the pool and you specify a payload size that exceeds the length of one of the pbuffs in the pool, they make linked lists. They link to one another and you use a bunch of them. Okay. In any case, right here is where we're creating the data structure that manages information transport through our stack, through the LWIP stack. Okay. All that we're saying is this is a transport pbuff. It's this big. Get it from RAM. What we're then doing, just as a matter of convenience, is we're creating a local pointer to a character, and we're assigning it such that it points to the same place as the payload field of the pbuff that we just created. So when we dereference REQ there, we are in fact also dereferencing. We're pointing to the same memory address as the payload field of our pbuff. Just makes things a little bit more tidy. We don't have to do the arrow thing every time. Okay. What we then do is clear the payload of this pbuff, just to be obsessive. Okay. So we're using a memset, right, pointing to the payload, the beginning of the payload of that pbuff. We want to set everything to zeros, this many bytes. We then populate the payload with some information. We do this with some familiar looking C string formatting. So we say snprintf, here is the address to which we would like to write. We'd like to write this many bytes. And here's what we'd like to write. Two strings, string, colon, string, new line. The first string that gets populated there is going to be our IP address. We wouldn't have to do this. It's just so that when we receive a message on our laptop, for instance, it tells us the IP address from where it came. Followed by the contents of the PT serial in buffer, whatever the user typed in. So if we typed hello and clicked send, then what we would receive is IP address, colon, space, hello. And then we actually send this message by way of the LWIP function send_to, which as an argument takes the protocol control block, takes the pointer to the pbuff, the destination address, and the destination port. This sends everything off. We free the pbuff that we just created so that we can use it again, or in the event that we had actually allocated some memory, it frees that memory so that we can use that memory again. Check for errors, and then go back up to the top and wait for the user to enter something again. Questions about this? So it's nice because you can do, relatively speaking, pretty high-speed communication because there's very little overhead associated with UDP. The cost of that little overhead is you also don't get some of the nice features of, say, TCP. You don't receive any acknowledgement from the device to which you sent a packet. You just kind of dump it out and trust that it got there. You have no guarantee that if you are sending lots of packets very quickly to some destination, you don't have the guarantee that they necessarily arrive in the order that you sent them. They may occasionally arrive in the wrong order. You do have such a guarantee with TCP. On the other hand, it's speedy. And for certain kinds of applications, it's kind of all you need, right? This is also, I think maybe next time we'll have a brief conversation about network time protocol. Once you connect to a network time protocol is a mechanism by which you can ask a particular UDP destination address to tell you what time it is so that you can receive the sort of UTC real time by way of a UDP packet. We can talk through how to do that next lecture, perhaps. DHCP also occurs over UDP, by the way, when you're actually getting assigned IP addresses and so forth. Those are UDP transactions. What do people think? Questions about this? What else can I point you to? If you go find this file, which we could find here in a moment, this is where all of the configurations occur. You probably don't have to mess with very much. You could. Anything special about the CMake lists? Not really. Oh, there's something else to mention here, I suppose. These Wi-Fi chips, they require occasional tending. Your code has to go tend to them now and then. By which I mean, you know, if they don't receive some kind of, call it like a message or an acknowledgement every so often, they essentially assume, oh, I should just turn off. Right? And so they require occasional tending. You can do that tending using LWIP in a few different ways. The way that this demo does it is it links this Pico CYW43 Arch LWIP thread-safe background library. What this does is it does all of that occasional tending of the Wi-Fi chip in a background interrupt service routine. It actually makes use of the same infrastructure, that async context infrastructure that the Bluetooth library makes use of. But what this implies is that our application code need not worry about that occasional tending. Every now and then an interrupt's going to fire, it's going to do what it needs to do, and then we're going to come back to our application code. There are other options here. If we had instead linked thread-safe, or if we had instead linked the polling library instead of thread-safe background, then there is a LWIP function, I forget the name of it, but there's a function that our application code would have to call now and then, on the order of, I think, tens of milliseconds, if I recall correctly, some number of milliseconds. So what that might suggest is you would have some thread running, some proto-thread running, and in that proto-thread you would be calling this function. It makes us responsible for this tending, but it also perhaps, I don't know, eliminates some of this background infrastructure. I don't know, maybe for some applications that's important. The third library, just incidentally, is if you are incorporating LWIP into FreeRTOS, the real-time operating system that a lot of folks use, there is a version of this that is compatible with FreeRTOS, where all this tending stuff gets sort of consolidated into its own thread in the FreeRTOS infrastructure. We're using thread-safe background here, and I expect probably most of you would for your projects. Okay, thoughts? Yes?
Where can we find the Wi-Fi?
I will push this to the course demo code. I haven't pushed it just yet, but Bruce has some great examples like this as well. Yeah. Okay, anything else? Otherwise, I will be in lab this afternoon. I'll see many of you then. I'll see the rest of you on Wednesday. Please sign up for a final demo if you haven't already. Okay.